Ever wondered why an apple falls straight down and not sideways? Or how a rocket escapes Earth's gravity? These seemingly disparate events are all explained by one incredibly powerful set of laws, Newton's laws of motion. But how exactly are these laws used in our everyday lives, and in ways you might not even imagine? That's what we're diving into today. Before we get into the how, let's do a quick recap of what these laws actually are. Newton's first law, often called the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Think of a hockey puck gliding across frictionless ice. It'll keep going until it hits something or friction slows it down. Newton's second law tells us that the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to its mass. In simpler terms, F equals ma. A larger force will cause a larger acceleration, and a heavier object requires a larger force to achieve the same acceleration. Pushing a shopping cart, for example, demonstrates this. A heavier cart requires more force to push it at the same speed as a lighter one. Newton's third law states that for every action, there is an equal and opposite reaction. When you jump, you exert a force on the earth, and the earth exerts an equal force back on you, propelling you upwards. Okay, so that's the theory. But where's the rubber meet the road? Let's start with something you probably use every single day, your car. Newton's laws are fundamental to how cars function. The engine provides the force, F and F equals ma, to accelerate the car, A. The car's mass, m, plays a crucial role too. A heavier car requires a more powerful engine to achieve the same acceleration. And when you hit the brakes, friction provides the opposing force, causing the car to decelerate. Even the seatbelt is a practical application of Newton's first law. In a sudden stop, your body continues to move forward due to inertia unless the seatbelt provides the necessary force to stop you. Beyond cars, consider the entire field of sports. Think about throwing a baseball. The force you apply to the ball determines its acceleration and therefore its speed. The angle at which you throw it, combined with gravity, another force, determines its trajectory. Newton's laws are at play in everything from the swing of a golf club to the flight of a basketball. Now, let's look at something a bit more complex, rocket science. Getting a rocket into space requires overcoming Earth's gravity. The rocket's powerful engines expel hot gas downwards with tremendous force, action. According to Newton's third law, this creates an equal and opposite reaction, pushing the rocket upwards. The sheer amount of force required highlights the relationship between force, mass, and acceleration as described in the second law. The more mass the rocket has, the more force is needed to accelerate it. But it's not just about brute force. Newton's laws are also critical for calculating trajectories and orbital mechanics. Scientists use these laws to precisely predict where a rocket will go and how to adjust its course. This is essential for everything from launching satellites to sending probes to other planets. Think about bridges and buildings. Civil engineers rely heavily on Newton's laws to ensure structural stability. They need to calculate the forces acting on the structure, including the weight of the materials themselves, as well as external forces like wind and traffic. By understanding these forces, they can design structures that are strong enough to withstand them. Without a solid grasp of Newton's laws, bridges would collapse and buildings would crumble. Even something as seemingly simple as walking involves Newton's laws. When you take a step, you push back on the ground, action. The ground, in turn, pushes forward on you, reaction, propelling you forward. The friction between your shoes and the ground is also crucial, providing the necessary force to prevent slipping. Let's move into the digital world. Video games, simulations, and even the animation you see in movies often rely on physics engines that are based on Newton's laws. These engines simulate how objects move and interact in a virtual environment, creating realistic and believable experiences. Whether it's a car racing game or a space exploration simulator, Newton's laws are working behind the scenes to make it all possible. And it's not just the big things. Newton's laws are at play in smaller, more subtle ways too. Think about the design of a chair. It needs to be stable enough to support your weight. This involves understanding the forces acting on the chair and ensuring that it's designed to distribute those forces evenly. Even the simple act of opening a door involves applying a force to overcome the door's inertia and move it. Newton's laws are so fundamental that they're used in countless other fields, from medicine to manufacturing. Doctors use them to understand blood flow and biomechanics. Engineers use them to design machines and tools. Even artists use them to create sculptures and installations that defy gravity. The beauty of Newton's laws is that they are universal. They apply to everything from the smallest atom to the largest star. They are the foundation of classical mechanics and provide a framework for understanding the physical world around us. While Einstein's theories of relativity have expanded our understanding of gravity and motion, particularly at very high speeds and in very strong gravitational fields, Newton's laws remain incredibly useful and accurate for most everyday situations. So, the next time you see a plane flying overhead, a car speeding down the road, or even just an apple falling from a tree, remember that Newton's laws are at work. They are the invisible forces that shape our world and make it possible for us to understand how things move and interact. With that said, thanks for watching, and until next time.